Welcome to this month's edition of a neuroprosthesis seminar. It's my pleasure today to introduce our speaker for February, Dr. Will Durfee. He's familiar to a lot of us in the room for a lot of years. Will is a professor and director of design education in the Department of Mechanical Engineering at the University of Minnesota. And his education includes an undergrad at Harvard, graduate school at MIT, and he's also the recipient of a number of teaching and mentoring awards, including the Minnesota State Council on Disability Educator of the Year Award and the University of Minnesota Outstanding Contributions to Undergraduate Education Award. So it's been active for a long time in the field of rehabilitation and particularly functional electrical stimulation and orthoses and the mechanical design of orthoses, medical devices, rehab engineering, and biomechanics and physiology. So if you don't learn anything from this morning, it's your own fault. So without any further introduction, I'd like to introduce Will Durfee.
Thanks, Ron, and thanks for inviting me. And it's terrific to be back in Cleveland and to catch up with old friends and to meet new friends. It's been about, I think about 8 or 9 years since I've visited the facilities here in the Cleveland area, and it's always such a refreshing and invigorating opportunity for me to kind of learn kind of where you folks are at. So I always come out of these meetings here in Cleveland feeling newly refreshed. So I'm looking forward to both showing you a little bit about some of the things that I'm doing this morning and to meeting some of you later in the day. Just a little bit about where I come from, the University of Minnesota. For those who haven't been there, that's our building down on the lower left, although like Cleveland, there is no snow there now as well. The University of Minnesota is I think Ron was telling me, a Case Western Reserve. There's something like, I don't know, you're saying 5,000 or 6,000 undergraduates. That would be a small little drop in the bucket. We're the fourth largest university in the country with a large number of students. One of the interesting things about the University of Minnesota, which is terrific for designers like myself, is that we do have so many disciplines, and so the possibilities of collaboration are really quite exciting. Quite exciting there. We have kind of the sweet spot, like this place. We have the sweet spot where the engineering school and the medical schools are co-located, and as you know, that's the physical proximity is critical for substantive collaboration between fields. And then the other part that is exciting about the Minnesota areas is our MedTech industry, which is core to the state of Minnesota. So within the campus, within 50 miles of the campus, there are about 450 MedTech companies, including large ones like Medtronic, which is the largest MedTech company in the world, and small, tiny startups doing. Our core areas are cardiovascular, and then our second core area is neuro among the big and small companies. So it's a pretty exciting place to do MedTech. Of course, we're very proud of Medtronic coming out of the University of Minnesota. Earl Bakken, in his garage on the right, his job was to go around the university hospitals fixing equipment. And Walt Lillehei, who's in the middle, is the leading cardiovascular surgeon at the time. And what you see on the left is the early days of pacemakers, where you could go as far as the extension cord would let you go, which was also problematic when the power went out in the hospital. So Lillehei asked Bakken if he could do anything about that. Bakken, at the time, subscribed to Popular Electronics. And just a few months before, there was a circuit on the cover for an electronic metronome. So he said, pacemaker, metronomes. He reconfigured the circuit into a box with a little battery, brought it to Lillehei. They had it on a dog model. A couple days later, Bakken came in 3 days later to see how the dog was doing. The table was clear. There wasn't any equipment around because Lillahai had taken it up and installed it in a 7-year-old boy the night before. So this was back in the days pre-strong IRBs and so on, when you could really do cowboy medicine. But that was the genesis of the Bakken. And if you ever happen to be in Minneapolis, I highly recommend, especially for this audience, the Bakken Museum, which is called the Museum of Electricity and Life, which is a remarkably wonderful history of the connections between electricity and medicine, and many of the it documents actually many of the devices and the technology and the science right here that came out of right here at Case Western. Then I'd like you to come, and I'll leave a few flyers. And every April we have a really fun MedTech Conference, 3-day immersion in medical devices. That's kind of sort of a mix between maybe what you see here at the Cleveland Clinic in their Innovation Summit, and an academic conference and a clinical conference. So if you have any interest at all in MedTech, definitely do stop by for our conference. All right, so I'm going to talk today a little bit about hybrid FES walking, talk about muscles, and then I'm going to spend predominantly time talking about fluid power. And as we get there, I'll explain why I'm pretty excited about fluid power, including in air-powered AFO. Try to give you some of the background to fluid power on a human scale with tiny hydraulics, a little bit on a hydraulic ankle-foot orthosis, and then some tiny power supplies. So that's kind of where we're headed over the next 45 minutes or so. So muscle-powered orthoses, I'm actually going to kind of, even though this may be a area that you're most interested in, I'm just going to kind of skim over this area for you, since it's hard to come up with anything new and different from what's going on here at Case. But I think the approaches that we have for this might be a little bit different. So we've been working for quite some time in hybrid systems that combine orthotics and electrical stimulation for walking. And one of the reasons why we are sticking to hybrid systems is that we only do surface electrical stimulation. And so this thought that these systems for walking, think about them more like an exercise machine that might be periodically used than a permanent assistive device. So once you say, okay, it's going to be surface stimulation, then you're immediately at a disadvantage because you do not have good access to the suite of muscles that you want, and you are immediately at a disadvantage because of the kind of the additional stuff that goes along with this exercise equipment. So here's one version which we worked on some time ago that is has controllable friction brakes at the joints. So the idea is you have an exoskeleton that you can lock and unlock the joints for body weight support, but at the same time you can control swing phase trajectory by manipulating the control to the friction brakes. Kind of like speed of a bicycle going downhill, where gravity pushes you, you manipulate the handbrakes. Here, the turn on the muscles that drive the limbs, and then you regulate the limbs during swing phase by regulating the friction brakes. And so this is kind of what that looks like in terms of gait. And what's interesting about this is I think it's the smooth knee extension, which comes about because of that regulating the brake. The same subject in using a without the brace and just a regular FES system tends to have very sort of snappy knee extension, but here we can do a fairly good job of controlling the knee extension. Now these systems are the traditional way back Ljubljana style, where the flexion is done with a reflex response, so that you trigger the flexion with the peroneal nerve. That has its problems. Works on some people, but can accommodate over time. Other people, it doesn't work. Highly variable. So as a consequence, we're looking at new systems now that basically do not rely on the muscles to provide the flexion. And so these are the systems that we're calling the energy storing orthotics. So the idea is to drive the entire mechanical part of the gait with knee extension. The reason why knee extension is a good one to use is that the quadriceps have a considerable amount of both energy and power in them. And then for surface stimulations, if you're going to self-don electrodes, that's probably the easiest muscle for someone with spinal cord injury to access. So the idea, and in this picture, the thick black line is the orthosis. So the idea is that the orthosis holds the leg in an equilibrium position that's flexed at the hip and the knee with elastic energy storage elements. Then with the stimulation of the quadriceps, the knee extends, storing energy in the springs about the knee, but then also storing energy in a bolus of compressed air with a small pneumatic cylinder. Then later in the cycle, you can release that bolus of compressed air up to the hip to extend the hip, and thereby getting hip extension and storing energy in the hip springs, and then you can release the knee and the hip and get flexion at the hip and the knee. So the idea is, I mean, for very primitive walking, straight line walking, you really only need hip flexion, hip extension, knee extension. You lock the ankle. So that's kind of the minimum that you need for forward mobility. Recognizing that systems like this are not going to get you, complete walking in any situation, up and down stairs, across rugged ground and across territory, but sort of simplified systems. So one of the things that if you're going to drive the system with the quads, how much energy does the quads have? So we did a number of studies looking at essentially fatigability of the quads, but really with this idea of extracting a certain number of joules per step cycle during leg lift kinds of activities, and essentially found out that you could get about maybe 25 to 30 joules per cycle fairly consistently. And so this is kind of a design parameter as you're going ahead in terms of designing the system. You say, okay, you can extract 25 joules per cycle out of the quads. Now design your system around that for operation. So part of that is, so I guess, okay, so we were assuming 21 joules per cycle, and then divvying that up amongst driving what it takes to drive the various elastic elements and so on. So it's kind of a system level approach to the design. A lot of the details are in the paper cited. Be happy to talk more about it offline for anyone that's interested. Then building up our system, we pretty much build it up around off-the-shelf kinds of components for convenient mounting solutions. A couple of the technical details that I think are kind of interesting. One is these elastic storage elements. It turns out that if you want to store elastic energy, stretch energy, and you look across all available materials, you can do no better than rubber bands for storage element per weight. So if you want to make a spring, if you want to make a light spring, do not make it out of steel. Do not make it out of carbon composites. Make it out of natural latex rubber. The other interesting thing about natural rubber is it's got very high elongation, 600% strain rate compared to things like composites or steel. It does have downsides, so it's got not a long cycle life, so it tends to get brittle, and then there tends to be hysteresis, so they are not as efficient as say a steel or composites. And what this chart on the lower left is if you plot all materials on a energy density both by weight and by volume, then it shows that up on the upper right in yellow are the natural rubbers. Lighter and smaller in volume goes up to the upper right in terms of picking material. Then the other interesting component, and I think you use some of them in the technology around here, are wrap spring brakes in order to hold the system upright. So for standing, certainly, and for slow walking, there's a considerable period of time when the knees are in a extended and locked position. And so it doesn't make a whole lot of sense to have either electrical energy or muscle energy providing that anti-collapse support. So this is where wrap spring brakes are pretty interesting technology because they are extremely light for a strong holding torque. So if you want something that locks, that can withstand a lot of torque and is lightweight, it's hard to beat them. The other interesting thing about these is that of all the technologies you can think of for doing lock and unlock, this is one of the few that can, you can unlock it under load without a lot of effort. If you think of something like a pin in a slot, and then you're pushing against that pin, there's a lot of friction. It's going to take a lot of oomph to pull that pin out. This does not have that. Unlocks very well under load, which makes sense. The third interesting thing about it is that they're one way. So that makes them a nice application to things like orthotics. So they prevent collapse, but they're free in extension. So that means in things like if you're using it for the knee and extending the knee, you don't have to apply any power to them because they're free to do the extension but prevent the collapse. All right, so
when that
yes.
tightens up, it just tightens up around the shaft.
Yeah. Oh, thank you. I was going on and on about all of the wonderful attributes without explaining how they work. So think about it's almost like a Chinese finger torture. When you stick your fingers in and pull it, it tightens down on your fingers. So this is a rotary coil spring where if you run the spring in its coil direction, then it'll tighten down on a shaft. So you've got two shafts sitting next to each other, and if the spring is loose, one shaft can rotate. If the spring is tightened down, then it locks the two together. And there are some design details. For example, the springs have to be very precise. The tolerances between the springs and the shaft need to be it's very, very tight, down to sub-thousandths of an inch to get the whole thing to work properly.
Can these fail when they accidentally lubricating them, or?
So if you drop, if you notice the friction coefficient mu is up there in the exponent where things are very sensitive. So if you put a drop of, if you happen to be squirting WD-40 in them, then it's going to be much more slippery for sure. Yep. Computer control and so on. So I know it's like all people who struggle with computers. It's there, and we struggle with it, of course. This is a small study where we're doing two subjects, and what we learned from the first subject, who you see here, is that the original concept of using the knees to drive the whole system turns out to be not the way to go, but not for the reason that we thought. We did all kinds of dynamic studies and all kinds of very careful engineering calculations, but it turns out that the flaw in this system is something that is very subtle, can escape engineers, but that perhaps physical therapists would know instantly, and that has to do with the alignment of the orthosis to the user. And it turns out that the way this system is configured is that you need to. So here's the piston on the knee. You need to extract. You need to displace that piston the whole way in order to store all the energy that you need to store. And it's quite sensitive to what's going on at the end, because with pneumatics, if you're storing energy in a compressed gas, it's that last little bit where you get most of the energy. And so it turns out that if you're just a little bit off in the alignment of the orthosis to the user, or if your orthosis structure flexes just a little bit, then you are not able to capture all the energy that your very careful mathematical equations said you were going to capture. Yep, sure. That let me go back to. So the question is, how's the knee influencing the hip? So it goes back to here. So the knee piston during extension, you store, it's compressing and store gas, and then in a little tiny accumulator, and then it's a valve that releases that compressed gas into the hip. So store it in a tank.
You feel the hip one.
You don't feel the. So it's so you compress the air by extending the knee, and then you release that compressed air into the hip one. So it's almost like a little pump to some extent. Yes.
Does it drive flexion too? So it drives the flexion and extension?
No, the flexion is done with flexion is done purely by the rubber band. So the elastic storage elements. Yep. Mm-hmm. Yep. And the reason for that, of course, is again with surface stimulation, activating hip flexion or knee flexion is problematic. So therefore, you have to look towards other solutions. So the current solution and what we're doing is to use a tank of compressed CO2 to drive the hip. Turns out that to drive hip extension. Turns out you don't need a lot of energy to drive hip extension, and so the added weight of a compressed gas, or the added weight, you could do it with a battery electric motor system, is going to be reasonable compared to the weight of the overall orthosis. If you're using it to drive knee flexion or knee extension, then you're talking about significant amounts of energy, but you don't need a lot of energy to drive the hip. So same system, but rather than with the energy storage and the elastic elements, but now it's a tank of compressed gas that is driving the hip. So what I thought I'd do is to show you kind of behind the scenes a little bit, which I can do with this audience. We're just starting on this second subject now, but just kind of what one of the typical initial sessions looks like when you're in this field with Brian, our physical therapist, and Joe, our subject, and you can sort of compare it and see if these look like the first sessions that you have here with first subjects that have never stood before. So I'll just play about a minute of this.
I don't feel like the knee unlocked. Joe, you fine?
Yep.
Okay. Can we go left now?
Yeah. So in 3, 2, 1, go. I think I should increase the stimulation.
Yep, that's fine.
You think whatever stimulation we did is good enough, or?
You could
For
do
the quads, you mean?
You could do more.
Yeah.
They're coming in quite a bit later though. So like the hips break, the knee breaks.
He
and
feels
then
like
it
he's.
starts going.
Yeah. Are you fine standing?
Yeah.
He feels like. Sorry, I'm just saying he feels like. I feel like the release happens, and then I'm not putting him on the ground. I'm waiting for the stem.
Okay.
And I think that's what Joe's feeling is he's hanging out bent.
And then the
Yeah,
stem
that's
kicks in.
because there's a ramp up time. It takes 2 seconds to.
So anyways, that's just to show you that the same kind of things go on in FES centers around the world in terms of dealing with people. There's so many things around. You design all the systems, it all works out on paper, and then when you actually get them on actual people, it's sort of a different story. All right, so let's shift over and look at non-muscle powered orthoses, and starting off looking from a system level view of muscles as motors. Where very, very interesting motors, and they're a huge part of your body, of course, a very substantial part of your body weight. And internally, very complex molecular kinetics that lead to muscle contraction. But if looking at it from systems view, there's a number of sort of parameters about muscles that you need to think about if you're going to replace them with non-muscles. So one of the things is that they actually are not particularly wonderful in terms of power density. They're about the same as your automobile engine in terms of power density, and they're really lousy compared to a aircraft turbine engine. In fact, it's still quite remarkable that birds can fly on using muscles. And then in terms of their key characteristics, get about 25% efficient. The things that make muscle pretty interesting are the extensive infrastructure, and so that is the capillary system that's providing energy and taking away heat, and the neural control system. And because of that extensive infrastructure, that's where you get that exquisite control that is so challenging to replace with any artificial means, and probably is almost unobtainable to get the kind of exquisite control that the natural system has over muscle. Fatigues, but not just like battery fatiguing, fatigues in very complex ways. The last three, I think, are probably the most challenging for thinking about any replacement by artificial means, and really actually those last three are a big part of why users just aren't particularly interested in wearing orthotics a lot, and that's the fact that muscles are clean, cool, and quiet. And then the last one that I wanted to highlight, which is really intriguing, and I'll get back to this a little bit later, is the fact that muscles can be floppy. And so if you're talking about systems to replace muscle, especially orthotics, having them be floppy the way muscles are, as well as being able to drive the system, is extremely, extremely challenging. Okay, so let's talk a little bit about fluid power, because I want to, by the end, hopefully convince you that fluid power is a viable option for creating non-muscle powered orthotics. All right, so there's two main reasons why fluid power is viable. One is that it's small. So here's a hydraulic pump driven by electric motor, and there's the electric motor, and there's the hydraulic pump. Same wattage, same power. So hydraulic stuff is small compared to electric stuff. So that's one thing I want you to take away. The very, very simple mathematics. I mean, force depends upon the pressure in the area, and that means that kind of drives you, it actually drives you to big diameters because the forces go up as the diameter squared. So on the one hand, you want to go to big diameter. So for human scale things, you don't want those big diameters, and so what that means is you have to take advantage of the other side of the force equation, which is to drive the pressure up. And the one message I want to leave you with is that using hydraulics only makes sense if you operate them at high pressures. But it's really quite extraordinary. This is, they're building some new light rail system outside of our building, and that 5-inch cylinder can produce 275,000 pounds. And that's the reason why hydraulics are on big, heavy equipment, because if you had an electric motor driving the bucket down here, this would be a substantially large and heavy electric motor, which at the same time is a big, heavy thing out at the distal end, which means that the ones that are driving the boom and the stick have to be even heavier. So if you think about wearable orthotics and you want actuators out at the end, you want to have very lightweight actuators. But at the same time, hydraulics are capable of exquisite control, and I don't know if you ever sort of carefully watch what goes on in excavators, but you know, they'll have construction workers down in the hole there, and this thing with 275,000 pounds is within a half an inch of their head. So good control is possible with hydraulics. When you think about human scale applications, we are high torque, low velocity machines. And electric motors are low torque, high velocity machines. So they are the complete opposite of where we are, which means that if you go electric, you need some kind of transmission. You need a gearhead, you need something to have electric motors drive your orthotics. And that transmission needs to be co-located unless you want to go with some complex cable-operated system that is going to be problematic for multi-axis orthotics. Whereas hydraulics are inherently high-force, low-velocity actuators, so they are a nice match to human muscle, either hydraulics or pneumatics. So fluid power is good for human scale application because very high force to weight, very high force to volume, and you can transport the pressurized fluid through flexible hoses. But it's bad because as you go down to small sizes, the systems become inefficient with drag losses through the hoses and drops across orifices. Nobody wants an orthosis that's going to be dripping oil on the ground. That's a category killer. And you can't buy the kinds of things that you need off the shelf, unlike in the electric motor system, so it makes a little bit of a challenge. All right, so replacing muscle with fluid power, it's about the power supply, it's about the actuators, it's about the packaging, and it's about the control. And I'm going to talk a little bit about the power supply and kind of packaging actuators and not about the control. I think the control is sort of far off there. It's a solvable problem, but not a rate-limiting step at this point in the development. So there are, of course, lots of non-muscle powered orthotics out there, some fluid power, some not, and as you know, there's been a wonderful rash of electric motor powered walking systems for lower legs, and I don't know if you're doing clinical trials with any of these now. So I think what I say is that there's plenty of precedent out there for non-muscle powered walking orthotics, and plenty of precedents for their acceptance in the user community. The work I'm going to talk about is part of a center that is a 7-university consortium headquartered at the University of Minnesota in fluid power, where we're looking at fluid power across the whole scale of weight and power, from wind power machines down to micromedical devices. And the part of the center that intrigues me and where I'm involved in is down here on the human scale, which is in the area of 10 to 100 watts. So that's 10 to 100 watts in terms of an assistance machine is quite would be quite a remarkable addition to your normal power. So when you're walking, you're expending maybe 100 watts. Athletes are up at 300 watts. So an additional 100 watt is quite a remarkable amount of power to add to a human system. We're working on ankle foot orthotics as a test bed for exploring tiny fluid power. And so the reason is that the lower limb is cyclic compared to the upper limb that's non-cyclic, so that makes things easier because you kind of know what the lower limb is doing. The ankle is particularly intriguing because it's got a reasonable range of motion, reasonable torque, about 70 Newton meters of torque, and then it's got very stringent packaging applications. So you talk about stuff down on your foot. You have to be, it keeps you honest about size and weight for sure. And then the power is kind of interesting. Your ankle is about 13 watts on average, but peaks to 200 watts. So that kind of makes it intriguing for thinking about fluid power systems using concepts of hydraulic launch assist. So this idea that you store energy in an accumulator and then you release it rapidly. Turns out that just the same way that roller coasters are launched with a hydraulic launch assist. Now, it turns out with fluid power, you can get very high power density, which means releasing power quickly. So that's sort of an intriguing match to what's going on down at the ankle that gives you this little burst right at toe off. So for those reasons, that's the joint that we've chosen to take a look at for a test bed to explore tiny fluid power. So here's an example of a pneumatic foot orthosis. This one is headquartered at University of Illinois under the direction of Dr. Liz Shaw-Wexler, who they're part of the center, and she and I are collaborating, and a couple of other universities in the center are collaborating on this ankle orthosis, but the pneumatics lead is going on at Illinois. So our design goals is a kilogram. A kilogram is about what you can tolerate on your foot. That's about a heavy hiking boot. And that it can fit under the pants, goes about 10,000 steps, and is quiet and is not exceptionally hot. So those are the far-reach design goals, and I'll tell you now that we have, trying to think if we've hit any of those goals yet. We have not hit any of those goals yet. Just truth in advertising here. So here's what that ankle-foot orthosis does look like in use on an individual with plantar flexor impairment. This particular one is driven by a bottle of compressed air that gives about 2,000 steps. And what you can see over here is this is the ankle power, and this is the normal toe-off push, that normal plantar flexion push. This particular individual had essentially no plantar flexion push, and the active ankle orthosis did restore that. And as far as we know, this is one of the few, if not the only, untethered powered active pneumatic ankle orthosis that's out there. There's plenty of ones that are tethered, but the whole business of untethered turns out to be more challenging.
Does that run into a problem when you're actively using it with the CO2 cooling your actuators? You have to heat your actuators?
So the question is, does the CO2 expansion, does it cool all the actuators? The answer is it doesn't impact it that way, but it does lead to inefficiencies when you have that expansion. So the actuators are pretty robust to the types of temperatures that come out, but you do lose energy with that cooling. There are a number of interesting tricks that you can, well, not tricks, but smart design choices you can make with this. So for example, because the plantar flexion torque, the toe-off one, is so much higher than the dorsiflexion torque, you can use the exhaust gas from your plantar flexion to drive your dorsiflexion and save a considerable amount. And then other versions of this that Dr. Schau-Wexler and her team were working on did energy capture. And so at heel strike, you can compress more small bladders and use that captured energy to actuate your ankle-foot orthosis. The next version of that, right now we're using commercial air motors, and actually this one is SMC. We were talking earlier, the current version uses an air motor from Parker. They make some pretty good, for a local company, they make some pretty good small air motors, but we're moving towards a custom one built by our colleagues in the center at Milwaukee School of Engineering that can do a better job of optimizing the torque levels that we need for the ankle and at integrating the various valves and silencers and other kinds of components that you need in the fluid power system. So the one on the right is a mock-up, but that should be approaching reality about June of this year. All right, let's take a look at tiny hydraulics now compared rather than pneumatics. So pneumatics has two issues. One is it's more challenging to bring up to very high pressures, and two, the fact that air is springy makes it more difficult to control because you've got this big spring sitting in your system. So with tiny hydraulics, there's kind of two questions that we're trying to answer. One is, hydraulics is wonderful for this big stuff. You know, how small can you go? Does the advantages of it still hold for small stuff? And then second, on a design question, when does it make sense to make these powered systems out of hydraulics and compared to electromechanical? So there's plenty of electromechanical orthotics out there. There's the iWalk foot ankle out there now. There's the various electric walking systems. So you have to have some advantage over that in order to make any sense to go with hydraulics. And what I hope to convince you is that that yes, if you drive your hydraulics to high pressure, it does make sense to use them, or potentially makes sense to use them over electrics. So the way we did this was through a systems level approach with a considerable amount of mathematical modeling of fluid power systems in order to predict their weight and efficiency. And I want to give credit to Zhiqing Cheng, who's an absolutely wonderful PhD student who's been doing a lot of this work. So you can do things like model cylinders, and you can do things like say, okay, if you're going, what's the weight of a cylinder? Well, if you're going to run it at this pressure, it's got to have a certain wall thickness or else it's going to burst. And then you can, if you look at the cylinder rod, if it's going to push a certain force, then the rod has to be a particular thickness or else it's going to buckle when you push on it. So you can come up with, use fairly standard order of magnitude type of equations to get the fundamental mechanics behind these things. And then, so it's kind of interesting what you come out with sort of quickly is this really, you wouldn't think it, but that rod coming out of the cylinder turns out to be a weak link because you want to have fairly long strokes and very high forces, so you need a big thick rod like this. But if you have a big thick rod like this, and this is in fact what goes on next time you see an excavator, you'll see that they're essentially rams where the diameter of the piston is about the same as the diameter of the cylinder because they're almost one-way devices if you sort of take a look at how they operate. But a one-way device like this means that when you pressurize this side for the retraction, you get almost no force whatsoever. So for things maybe like the ankle where you do have differential torque, it might make sense, but it turns out to be a little bit of a limit, which actually brings you back potentially to biomimicry solutions with things that are more tendon-like and single-acting cylinders. So that's sort of an area that we're exploring. So one of the things that this mathematical modeling did, is it just all theory? But it turns out that PS, we took catalog data from about 186 commercial cylinders, predicted what they should weigh, and looked at what our mathematical model said they should weigh, and we're right on. So that says that these equations do make sense. And what's interesting about the expansion down here is it says that the actual weight of smaller cylinders are heavier than they should be. And that's because a real component has fittings that go along with it, and all the little things that are needed to screw the lines in and so on start to add more and more to the weight as you get down to the smaller cylinders. And what that says is that there's opportunities for thinking of hydraulic systems not as single components that you bolt together, but rather as an integrated system. So we'll talk a little bit more about that in a couple of minutes. Then efficiencies, there is right here on the seals, two things can happen. Fluid can leak, and then you can get friction. So in one case, you lose volume, the fluid. The other case, you lose force because of the friction. So those are become extremely important as your size gets small. And interesting enough, what this is, this shows bore size in millimeters. So this would be a 4 millimeter diameter piston. What it shows is that as you get down very small and look at the overall efficiency, the efficiency drops off. But it turns out that you do better if you don't have no seals at all around the piston. So the green and the blue case, you do better to have no seal at all, just a tiny gap, and let the fluid flow through the gap, because the amount of friction by putting a seal in there turns out to be a lower efficiency. The best case is that light green one, but you don't want that, because no seal off of the green one on the rod means that the oil is dripping out onto your leg. So that's probably not a case that you want to do. So, there's, as you start doing these scaling laws, sort of these interesting things come out that are a little bit unexpected. All right, so comparing electric to hydraulic. If you have do you go with motors or do you go with cylinders? So battery, motor, gear, and you need that gear to get you to the high torque, low velocity, or pressurized fluid and cylinder to give you the useful rotary mechanical power, where that gear is heavy, cylinder is light. So we did a systems analysis comparing electric to hydraulic, and we are, for the moment, ignoring this side and looking just at conduit to cylinder and wire electric motor to a ball screw for the transmission, because ball screws are the lightest transmission available. So that's kind of best case. If you're doing an electromechanical system, you want to use a ball screw. So what we did was to specify output force and power, and we were specifying them around what it takes for the ankle. Design the electromechanical system on paper using best available components, then calculated that weight, then designed the hydraulic system with the same output, the same efficiency, and then using our equations for the hydraulic system, predicted what that would weigh. And the answer is on the plot at the bottom. So along the x-axis, you see the power of the system, and the y-axis is the weight of the system. What it says is that if you have a 100-watt system, your electric system in red is going to weigh about 300 grams, more or less. If you run a hydraulic system at 100 psi, it's going to weigh about 800 grams. It's a log-log scale. So running hydraulic systems at 500 psi makes no sense whatsoever. If instead you run it at 1,000 psi, then your hydraulic system is going to weigh about 60 grams. So the message here is that you need to have your hydraulics running minimum of 500. 1,000 is better. Higher than 1,000 is even better than that. But you can't ignore the power supply, and I'm going to talk a little bit about the power supply in a minute. So here's an early hydraulic AFO prototype where we're well, for the power supply, we're going battery to electric motor to pump to conduit to cylinder. So here's why you can't use off-the-shelf components. This is a little demo system which can lift you up. It's pretty impressive in terms of force. The whole thing fits on an 8.5 by 11 piece of paper. The actual weight of the components is about 1.2 kilograms. The weight of what's sitting on here is 2.5 times that. And that's because what you see in the picture is dominated by fittings and hoses, all the kinds of additional stuff that you need to get these hydraulic systems going. So one of the things about that this is telling you is that if you want an effective wearable system, you're going to have to come up with a solution that does not have those fittings and hoses. Here's generation 1 of our ankle-foot orthosis, which is that same demo essentially reconfigured onto a ankle-foot orthosis, and it can lift you up on your toes, so it's sufficiently strong to lift you up on the toes. Cannot go the full velocity of gait, and as you can see, it's way off of our target weight. And so the question is where to go from there. Now we're where we are right at this instant in February of 2012, and this is pretty much where we are going, where the diameters of these pistons are correct for giving you 100% of your ankle torque. So this system will give you 90 Newton meters, which is where your ankle torques. This system will not give you the full speed. On the top right, the green is your ankle speed, and we, for purposes of demonstration, are trading off speed to get that full torque. But what'll sit at the ankle should look not that, won't look quite this good, but not that dissimilar to what you see here. And we do have this co-located vision. You know, artists rendering are wonderful. Everybody's going to sit right there at the ankle. But we've come to the conclusion that the source of the pressurized fluid is going to, for the moment, not sit down at the ankle, because that is going to be too heavy. So that would have to be someplace else. And there's a lot of things about that choice that we can talk about later. All right, how do you generate the pressurized oil? Turns out that small piston pumps are because of their high efficiency is the way to generate pressurized oil. There are a couple of commercial options, a Japanese company down the lower right, Parker Oildyne up on the upper right, which are in the ballpark but not exact. So we are right now designing custom versions of small piston pumps to give us that. I think I neglected to tell you in the last slide, we're going to run our systems at 2,000 psi to get those diameters. Okay, so let me close out and go back to that pneumatic system and talk about how to get. You notice that tank of compressed CO2 gave you 2,000 steps. So how do you get to that 10,000 steps, and what if you want to get rid of the battery? So let's get rid of the battery, and the way we're going to get rid of the battery is to look at energy density of power sources. So here's your cell phone energy density, and here's hydrocarbon fuel. It's just, there's a reason why our cars run on gasoline. It's just not even in the same ballpark for energy density. And then for the conversion of that energy density to mechanical, here's an electric motor. So these electric motors, this is allowed, not a great example, but here's a 1-watt electric motor. And here's a 180-watt internal combustion machine conversion. So in terms of power density, internal combustion engines are remarkably power dense. And if you look at going from hydrocarbon fuel to cold compressed air, if you can do this with 3% efficiency, you will do better than a battery through a electromechanical conversion to mechanical work out. So internal combustion engines, the efficiency process is not nearly as efficient as battery and electric motor, but because the energy density of what you start out with is so much higher that you can win on size and weight even if your conversion process is inefficient. So here's what you want to do. You want to build a tiny air compressor. And here's a tiny air compressor that is a free piston configuration with HCCI combustion. And I'll explain the latter in just a second, but let me walk you through this engine. So up at the top, you have the combustion chamber. So the fuel explodes here, drives this piston down. This piston, through a connecting rod, is connected to the compressor piston. So as this whole thing drives down, you compress air down here that goes off to a storage tank through a check valve. At the same time, you're pressing down against a spring, which rebounds it. The piston drives back up so that the new fuel air is squished, and it squishes till it explodes, and then drives it down again. So unlike a crankcase engine, this is a free piston engine. The reason why you want to use homogeneous charge compression ignition is that on the left, which is a normal spark ignition, as you get small, sparks don't work because the walls are so cool of the cylinder that the spark combustion quenches. Plus, as you get small, you can't put a spark plug in there. There just isn't room. Same reason why you can't use diesel. But homogeneous charge compression ignition, you basically squish the fuel-air mixture till it explodes, and at some point it's going to explode. And it's got another advantage that because the explosion happens all at once, all of the fuel is burned. Unlike spark ignition, where you've got flame propagation, you're always left with a little unburned fuel. And this HCI does work down to some earlier work at the University of Minnesota showed that you can get combustion in a cylinder as small as 2 millimeters this way. So designing this engine is a challenge. You've got to get the, you can either have a big engine running slowly to give you the power, or you can have a little engine going put, 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 put very quickly to get the power. So we're going small and fast. But you got to look at the engine dimensions, fuels, efficiency, the scavenging, the valves. There's a lot of details in designing this, this engine. So Lei Tian, the PhD student on this, working with my colleague Dave Kittleson, who's the engine expert. A lot of mathematical modeling, combustion, heat transfer, thermodynamics, piston dynamics. If you run the engine too fast, you don't give the fuel enough time to explode. So you compress it, but then it's going this way so fast it doesn't explode. You run it too slow, and then the fuel leaks by the cylinder. So you can't run it too fast, you can't run it too slow. And so I'll skip over a lot of these details. And again, it has to do with the type of fuel and fuels that can auto-ignite. But we've basically determined that about 300 hertz is the optimum speed for the 40-watt, more or less, engine that we're designing with essentially a kerosene fuel. So here's the prototype. It's about 5 inches long, and this, yes, noisy, smelly, hot. I'll explain that in just a minute. So this prototype, we're very excited because just about a month ago, it was actually able to compress air, which was very exciting, to 80 psi. We were predicting an efficiency of 5%. Our measured efficiency was about 2%, and that mostly has to do with the precision of the construction of the engine and the friction and leakage in the system. Both solvable problems. But as far as we know, this is the world's smallest air compressor, which has maybe not applications to orthotics because of that noisy and smelly, perhaps in rehab, but not on a daily use, but certainly has a lot of potential for things like handheld power tools. All right, so challenges in tiny fluid power, fabrication, so component integration, minimizing size and weight, precision machining. If you're going to have a sealless gap, that gap has to be down around the order of 10 microns or so. So precision machining. High pressures, as we said, so you're operating at 2,000 psi. How do you do the seals? Low frictions or a leak. How do you keep it safe? How do you get that 2,000 psi fluid? And it really is all about the efficiency. All these things really devolve down to how heavy the battery is or other power source, energy source you want to carry around. So the actual efficiency, you can design a really tiny system. It won't be very efficient, and the consequence is that if you want to go 10,000 steps, you have a heavy battery. So kind of looking at all that from a systems level. And then controlling not only performance, but controlling so that if you really want to get your system to last 10,000 steps, you're controlling for efficiency. Last couple of slides. I think this is an audience that does not need reminding that certainly going back to the orthotics land, most of the stuff out there is abandoned. And then the second thing, which I always show around my group, is that this really is the competition when you're talking about ankle foot orthotics. All right, thank you very much, and I would be happy to answer any questions.
Will, I'd like to thank you. Okay. Thanks very much. Here's a little token of our appreciation for this morning.
Thank you.
And we'll try to get the microphone to anyone with questions in the audience.
Yeah, very interesting presentation, thank you. That you make a really good case by the hydraulics, so I was wondering, as the systems go smaller and smaller, the diameters get smaller, then the pressure is going up. So what happens if you're given smaller? There must be some kind of optimum at level at which you can go, like if you go into microfluidics, there's no way you can, the pressure would be too high. I'm guessing the seals would be a problem.
Yep. So, yep. So the question is, what happens as you get really tiny? So small is good, but at some point there's a limit, and it turns out that once you start getting below about, if you take the case of a cylinder, about 6 millimeters, then the efficiencies drop way down. So about 6 millimeters is the limit. In fact, in the ankle orthosis, the mathematics says that our dorsiflexion cylinder should be about 4 millimeters, but that will be so inefficient that you don't want to go that small. And yes, there are microfluidics. The thing about microfluidics, they're essentially, the microfluidics is low pressure, so they don't have to deal with those kinds of things. Yep, so 6 millimeters if you want a number. I probably said 7, 8, somewhere around there. I think I said probably 6 different numbers in there, which says it's not an exact one, but yep.
Will you tend to emphasize in cylinder design the fact that you need to have the rod diameter and the cylinder wall dimensions, but I would think that the issue of the seal, you said if we don't have a seal, there will be leakage. Wouldn't that also drop down the pressure much lower than what you would love to have? I mean, if there is a leakage in the seal.
Yeah, no question. So gap seals. So what I'm arguing is that at tiny dimensions, you do better in gap seals than you do in a traditional polymeric seal. A great example of the effectiveness of gap seals are the company called AirPot, which is air dampers, and they're really remarkable devices that use a quartz cylinder, very precisely machined, and a graphite piston, very precisely machined, so that the air gap, it's a gap seal, which is on the order of, nearest we could extract out of the company, on the order of 3-4 microns. And it's quite remarkable. You can press that thing down and compress air and hold it for a considerable period of time, essentially no leakage. So gaps are possible with little or no leakage. Once you get above 20 microns in gap, then you don't want to do it, because then you lose so much. It's not so much you lose so much fluid going by that the whole system becomes inefficient. So if you're going to do a gap seal, it needs to be on the order of 10 microns for the gap. But then it is better because you lose on the friction. And all this, once you get to sort of the big off-the-shelf components, it doesn't matter. But if it gets small, it's the circumference to area. The circumference starts to get large with respect to the area. So what's going on in the circumference matters a lot.
I'd like to go back to your full leg orthotic for a minute. First, the movies you show demonstrate a remarkable, stable, smooth extension, I think. And you talking about some of the other challenges in the design, but I also noticed that you're having sort of a trunk piece for strapping everything in and putting some of the weight on the hips. Do you have plans, or can you comment on including trunk support or trunk stabilization to try to remove some of the reliance on the parallel bars? And because for the first video, for example, there was some pretty impressive stepping, but not a lot of trunk stability.
Yeah, so it really, I mean, certainly you can do trunk stability with E-stim types of solutions. I think for these types of systems that we're doing, that for someone who does not have, the higher level SCI does not have good trunk control, then I think having the TLSO, the fabricated trunk supports is going to ultimately be the simpler way to go. There's no particular reason for that first subject, no particular reason why that one couldn't use a walker, and probably just crutches. We just didn't work with that one long enough to go that far. But I agree with you that trunk stability, and even if you start talking about sort of complex schemes with crutches where you're lifting one arm up and you have disturbances and so on, I think we're going to leave that to you folks here that are leading the world in that. And when you come up with something that is compatible with the simpler systems that we have for surface stimulant, then we'll gladly take your ideas.
Yeah, I thought the talk was great. I'm kind of really interested in the manufacturing methods that you've used to produce these types of parts. I know there's probably so many specific little parts and methods that you're using to do it. So maybe just a brief overview of, what are the kind of the cost, time, precision, trade-offs that you have to make. I don't know, if maybe it's CNC or yak lasers or something like that you have to use to make these, really precise parts.
Yeah, sure. We're just getting into that now, and up to now we've sort of done more improvised kinds of things, but certainly for these systems of integrated hydraulics, we are going to go with, there's new additive manufacturing processes out there that you can build up parts out of titanium with very complex internal geometries and reasonable precision. For things like the cylinders and the gap seals, then you do have to go with traditional precision grinding and those kinds of operations. But for the ones where you've got sort of this complex geometry that you want to integrate into a ankle orthosis and internal chambers and passageways and so on, then the new additive manufacturing processes that can take those high pressures is the path we're going to go down.
So if we look at muscles, they're kind of organized to be very highly parallel and serial. Have you guys looked at, are there any kind of materials that we can fabricate, the memory changing, materials, things like that we could maybe take advantage of, kind of that steal from nature and develop that? Have you guys looked at anything like that?
Interesting to say, we actually are looking at some sort of intriguing things with arrays of parallel pneumatic actuators for, I guess maybe the best way to describe it is active clothing sort of things, and it actually looks fairly intriguing as a way of adding to the force. So arrays of tiny actuators. The serial ones, there isn't any kind of direct analog, and you may as well just have a sort of a long, if you look at a traditional serial, long stroke cylinder is going to do you about as good as a stroke. Because the thing about fluid power is that unlike muscle, you're not restricted to the extension length. So the reason why muscle cells are in serial, because you can only go so far before the cross bridges start getting out of alignment. But with cylinder, you can even think about cylinders that are tubes with discs in them where the disc is traveling a kilometer. But certainly the parallel die, and probably the thing that's going to hurt in the parallel side is that the advantage of parallel is you have lots of little tiny actuators, but now you're getting down to diameters where the efficiency starts to hurt you. Again, unlike muscles where the fundamental unit is tiny and efficient.
Hi, another question. I'm a little bit naive about the power requirements for generating the pressure in the hydraulic system for the ankle orthotic, but can you comment on the possibility of using or converting the power of the gait to move the ankle orthosis? Perhaps if the person is walking and maybe they just have foot drop, so only the ankle is affected, but the rest of their gait is good, and there's a lot of energy that could be harnessed. Mm-hmm. Would that be sufficient?
Yeah, I mean that's a terrific question, and there's been literally decades of research of attempting to harvest energy off of human motion, and there's kind of two pathways to it. One is for energy capture to run stuff. So run your cell phone from the magic shoe that captures the energy, and there's a little electrical generator and so on. That area actually has a kind of a new life to it because of the advances in piezo electricity generating materials that are coming out of new research in nanomaterials. So that for a while that looked like it was completely ridiculous now is starting to come back and is really a technology area to follow. Then the second is, okay, hey, your knee dissipates energy during gait. Let's just capture that and use that to to drive other parts of the system. The challenge is also in the efficiency of that round trip between capturing the energy and then storing it and then converting it back to actuation. Liz Shaw-Wexler and her group at Illinois did do quite a nice system that captured the dissipation at heel strike and used that to generate a lock-unlock mechanism for toe drop sort of thing. And that, it worked fairly well. So if you can get that round trip efficiency to close to 90-95%, then it's going to be feasible. But it's been tough to date. So I guess we're not looking at that area right now.
Okay.
Sorry, just real quickly. I think it's interesting that all the, another way to look at this would be the cylinders, right? They're linear, and so a lot of the joint motions are rotary. So another way would be, a lot of industries would be interested in a more high fidelity rotary seal that would allow, the elimination of placing everything at a distance from the joint. I was just wondering if you had thoughts on exploring that aspect of it.
Yes, a lot of thoughts actually, because we've thought about that a lot, and there's a couple different answers, but I'll try to keep it short. So one reason why cylinders are optimum is that if you look at the area to the circumference area, so circumference is the seal, and if you look at an area is about the pressure. So if you look at the circumference to area, you can't do better than a circle. And all rotary motors have some kind of veins or other sorts of things, and the sealing around the vein turns out to really kill. So those rotary air motors are terrible on efficiency, and rotary hydraulic motors, vein types, are low efficiency, which is why high efficiency hydraulic motors are actually a series of little pumps. There's these piston pump motors. Right, but you notice the configuration though, if you've got something that's on a ankle-foot orthosis, you've got that sort of the legs are long and narrow, right? So you've got a lot of area this way. So, big diameter hydraulic pneumatic motors are actually not a good match for joints, because then you end up, sort of going out like this. But you do have sort of this area going up and down. So even geometrically and fitting to the system, then linear, like muscles, are an intriguing way to go.
All right, I know we have at least one orthotist in the audience, so any questions? Any other questions? I just had I was gonna, before we break, I wanted to ask you to comment. You made a point of,
yeah.
You made a point of that co-location with the ankle joint was one of your design criteria. But if you look at that, excavator, the pump and the motor is back of the cab, and all the actuators are out near the dirt. So, how important is that co-location as a design constraint?
It's a design constraint that we are relaxing for the immediate future, because that we at this point don't see a way around being able to get both 10,000 steps and under a kilogram at the ankle. So then it's kind of wary. But on the other hand, if you for a piece of assistive technology on daily use, people don't want to have things that run up their legs, and strap to the ankle, just in terms of use and so on. So that is going to be a huge hit on acceptance. So unlike that's where people and excavators are different. So excavators have that internal thing that you can put on that, and that's actually one of the differences between orthotics and prosthetics. So prosthetics, you can move things proximally maybe, because you still have space to play with, but with orthotics you don't. So it's I think it boils down to a question of usability. It's kind of like everyone thinks that a backpack vacuum cleaner would be a terrific way to go, and you see some of them out there. But if you go out and interview cleaning personnel, they by and large do not like it. They don't want that thing on their back, even though you think it's a great idea. So it's going to be an acceptability thing.
Okay, well, thank you very much.